Good day, everyone, and welcome to our ODE series. So, in continuation, we are going to be talking about homogeneous differential equations. A differential equation of the form dy dx is equal to f of x comma y divided by g of x and y is said to be homogeneous if each term of fx comma y and gx comma y is of the same degree. So, take for example, dy dx is equal to 4x squared y plus 5y cubed divided by 3x cubed minus 2xy squared. If you take a look at the numerator of this differential equation, we have two terms, 4x squared y and 5y cubed. For 4x squared y, the highest degree that we have there, when you combine the x squared and the y terms together, we see that the degree is degree 3. And for 5y cubed, we also see that the degree is degree 3. So it's safe to say fx comma y is homogeneous since both of the terms, each term of the expression is giving us a function of degree 3. So for the denominator now, we have 3x cubed minus 2xy squared. If we take a look at the first term, 3x cubed, the degree of that first term is 3. And for the second term, 2xy squared, the degree is also 3. So it's also safe to say that g of x comma y is homogeneous. And hence, fx comma y and gx comma y, they are homogeneous, making the entire differential equation homogeneous. So if we have a homogeneous differential equation, we'll put y is equal to vx. So instead of solving, we can't easily solve it like this. So we have to find a way to simplify this equation. So to simplify that, we make y equal to simplify that, we make y is equal to vx. So on differentiating both sides implicitly, we have dy dx is equal to v plus x dv dx using product rule for the right hand side. So now this reduced equation, we have a reduced equation involving just v and x, and we can solve this equation using variable separation method, which we discussed in our last video. We are going to be showing this more in further examples, but before we dive into the working rule for the homogeneous differential equation, let's take a look at the test for homogeneity of a function. So to test for the homogeneity of a function, we say a function f of x and y is said to be homogeneous of degree n if the equation f of lambda x and lambda y is equal to lambda raised to the power of n multiplied by f of x and y. So if this holds for all x and y for which both sides are defined, the function f of x and y are said to be homogeneous of degree n. So to show this, let's take a look at the homogeneity of the following functions. For the first one, we are asked to test for the homogeneity of fx and y is equal to the square root of x raised to power 8 minus 3x squared y raised to power 6. So to test for the homogeneity, our f of x comma y, number 1, is equal to the square root of x raised to power 8 minus 3x squared y raised to power 6. So f of lambda x comma lambda y will just be equal to the square root of lambda x raised to power 8 minus 3 lambda x squared multiplied by lambda x raised to the power of 6. So our f of lambda x comma lambda y now becomes the square root of lambda raised to power 8 x raised to power 8 minus 3 lambda raised to power 8 x raised to power 2 y raised to power 6. Sorry, there's a mistake in what I wrote initially. So this should be lambda y raised to the power of 6. So let me rewrite that. Sorry. So let's write this as lambda y raised to the power of 6. So in writing this, we have lambda y, everything raised to the power of 6. So this becomes the square root of lambda raised to the power 8 into brackets x raised to the power 8 minus 3x squared y raised to the power 6. On further simplification, we have f of lambda x comma lambda y will be equal to lambda raised to the power 4, because when we find the square root of lambda raised to the power 8, we have lambda raised to the power 4, multiplied by the square root of x raised to the power 8 minus 3x squared y raised to the power of 6. So this becomes lambda raised to the power 4 multiplied by f of x comma y, and this f of x comma y is said to be homogeneous of degree 4. So that's how easy it is. So we see that f of x comma y is an homogeneous function. So the second example said f of x comma y is equal to 3x cubed plus 2y squared. So f of lambda x comma lambda y now becomes 3 into bracket lambda x cubed plus 2 into bracket lambda y squared. And this gives us 3 lambda cube x cubed plus 2 lambda squared y squared. If we try to factorize lambda out, we have lambda squared into bracket 3 lambda x cubed plus 2 lambda y squared. And this is not equal to lambda raised to the power n into brackets or multiplied by f of x and y. So we say the function f of x and y is equal to 3x cubed plus 2y squared is not homogeneous, since it does not satisfy the condition for homogeneity of degree n. So this is just another way for testing for the homogeneity of a function, aside looking at the degree of each term of the equation. So up next, I'm going to go to the working rule for solving homogeneous differential equations. So now to the working rule for solving homogeneous differential equations. The first thing we have to do is we are going to let y to be equal to vx. So that on differentiating y, we have dy dx is equal to v plus x dv dx. On doing that, we now separate the variables. Since we are going to be getting a function in v and x, we can separate the variables after successfully substituting y is equal to vx and substituting the value of dy dx in the original differential equation. After that, we integrate both sides, then we put v is equal to y over x to obtain our final solution in terms of y and x. So let's look at how this works. To start with, we have the differential equation dy dx is equal to y over x plus x sine y divided by x. So to solve this, you substitute y is equal to vx and dy dx is equal to v plus x dv dx. So on doing that, we have v plus x dv dx is equal to vx divided by x plus x sine vx divided by x. So on simplification, we have v plus x dv dx is equal to v plus x sine v. So we have v on both sides, so we can subtract them from each other. If we subtract v from both sides, we have x dv dx is equal to x sine v. Since we have x on both sides, we can now simplify this to be dv dx is equal to sine v. Now this looks like a function in v and x and one that we can separate. So using the separation of variables, we have dv dx to be equal to sine v. On dividing both sides by sine v, we have dv divided by sine v is equal to dx. So we know the next step is to integrate both sides, which we are going to be doing right now. But before that, 1 over sine v is cosec v, so we can write this as cosec v dv is equal to dx, after which we can now integrate both sides. So we have integral of dv divided by sine v is equal to x plus c. So we can write sine v as the integral of dv divided by sine v over 2 plus v over 2 is equal to x plus c. So we can simplify this to be integral of dv divided by 2 sine v over 2 cos v over 2, which is equal to x plus c. We can use substitution to evaluate the left-hand side of this differential, of this integral. So to do that, we can say let u be equal to sine v over 2. And we have our du dv to be equal to 1 over 2 cos v over 2. So our dv automatically becomes 2 du divided by cos v over 2. We can then substitute this to our integral, and we have integral of 2 du divided by cos v over 2 multiplied by 1 divided by u cos v over 2 is equal to x plus c. So we have integral of 2 du divided by u cos squared v over 2 is equal to x plus c. But also, we know that cos squared v over 2 is equal to 1 minus sine squared v over 2, and this is equal to 1 minus u squared. So we can write this to be integral of 2 du divided by u into bracket 1 minus u squared will be equal to x plus c. So we can go ahead to simplify this. So there's a 2 missing here. So this becomes integral of du divided by u into bracket 1 minus u squared is equal to x plus c. So on decomposing the left-hand side using partial fraction, we have this to be equal to integral of 1 over u plus u divided by 1 minus u squared du is equal to x plus c. So you can go ahead to simplify this. This becomes the integral of du divided by u plus the integral of u divided by 1 minus u squared du is equal to x plus c. On evaluating this, we have ln u plus minus 1 over 2 ln 1 minus u squared is equal to x plus c. So this becomes ln u minus 1 over 2 ln 1 minus u squared is equal to x plus c. We can then simplify this to be ln u minus ln 1 minus u squared raised to power 1 over 2 is equal to x plus c. Now, you recall that u is equal to sine v over 2. So we can substitute this to be ln sine v over 2 minus ln square root of 1 minus sine squared v over 2 is equal to x plus c. So this now becomes ln sine v over 2 minus ln square root of cos squared v over 2 is equal to x plus c. So this is ln sine v over 2 minus ln cos v over 2 is equal to x plus c. So this becomes ln sine v over 2 divided by cos v over 2 is equal to x plus c. So ln tan v over 2 is equal to x plus c. Now the next step is to substitute our v to be equal to y divided by x, such that we have ln tan y divided by 2x is equal to x plus c, and we have our final answer, the solution of the differential equation dy dx is equal to y over x plus x sine y over x. So let's take a second example. We have 2xy squared dy minus x cubed plus 2y cubed dx is equal to 0. So this is also a very straightforward problem. So we have our 2xy squared dy is equal to x cubed plus 2y cubed dx. You can make dy dx the separator formula such that dy dx now becomes x cubed plus 2y cubed divided by 2xy squared. On doing this, you can make our dy dx equal to v plus x dv dx, and also our y is equal to vx. So let's substitute that. We have v plus x dv dx is equal to x cubed plus 2 into bracket vx cubed divided by 2x to bracket vx all squared. So now we have our v plus x dv dx to be equal to x cubed plus 2v cubed x cubed divided by 2x v squared x squared, and this gives us x cubed plus 2v cubed x cubed divided by 2v squared x cubed. So we can factorize x cubed from the numerator and denominator. We have v plus x dv dx is equal to x cubed into bracket 1 plus 2v cubed divided by x cubed into bracket 2v squared. So we have 1 plus 2v cubed divided by 2v squared. You can further simplify this to be v plus x dv dx is equal to 1 over 2v squared plus 2v cubed divided by 2v squared, which gives us 1 over 2v squared plus v. So since we have v on both sides, we can subtract them from each other. We now have x dv dx is equal to 1 over 2v squared. Now we can separate the variables successfully here. On separating the variables, we have the x all over x is equal to 2v squared dv. So 2v squared dv is equal to dx all over x. We can now integrate both sides. We have integral of 2v squared dv is equal to the integral of 1 over x with respect to x. So we get 2v cubed divided by 3 to be equal to ln x plus c. So recall that our v now is equal to y over x. We can now substitute that to get 2 over 3 into bracket y over x all raised to the power of 3 is equal to ln x plus c. So we have 2 over 3 y cube divided by x cube is equal to ln x plus c. So you can further simplify this to have 2y cube is equal to 3x cube ln x plus 3x cube c. So we can rewrite this as 3x cube into bracket ln x plus c. And we have our final answer, which is the solution of the differential equation. So let's take one more example before we wrap up the video. So here's the third example. So we have y squared plus 2xy dx plus 2x squared plus 3xy dy is equal to 0. So this can be very tedious, but let's try as much as possible to decipher this. So we have dy dx. On rearranging this equation, we have dy dx is equal to minus y squared plus 2xy divided by 2x squared plus 3xy. From this, we see that every term in the numerator and denominator have the same degree, which is degree 2. Hence, this is an homogeneous, they are both homogeneous, and hence the differential equation is homogeneous. So we can substitute our dy dx to be v plus x dv dx. Then on the other side, we substitute y is equal to vx, and we have v squared x squared plus 2x into bracket vx divided by 2x squared plus 3x into bracket vx. So we can further simplify this to be v plus x dv dx to be equal to minus v squared x squared plus 2v x squared divided by 2x squared plus 3v x squared. Now x squared is common in every term on the right hand side, so we can factorize it out, and we have v plus x dv dx is equal to x squared into brackets minus v squared plus 2v divided by x squared into bracket 2 plus 3v. So I wrote cube here instead of squared for the 2x cube. So let's erase that off. And we have 2x squared here. So on simplification, we now have v plus x dv dx is equal to minus v squared plus 2v divided by 2 plus 3v. So we can subtract v from both sides, and we have x dv dx is equal to minus v squared plus 2v divided by 2 plus 3v minus v. So our x dv dx now becomes, we find the LCM of this, which is 2 plus 3v minus v squared minus 2v minus v into bracket 2 plus 3v. So this leaves us with minus v squared minus 2v minus 2v minus 3v squared divided by 2 plus 3v. So we continue. Our x dv dx is now equal to minus 4v squared minus 4v divided by 2 plus 3v. So we can move all the terms containing v to the left hand side and all the terms containing x to the right hand side. That's we separating the variables. So we have 2 plus 3v dv divided by minus 4v squared minus 4v is equal to the x divided by x. So we have successfully separated the variables in this case, and we can go on to integrate. So we have integral of 2 plus 3v divided by minus 4v squared minus 4v with respect to v is equal to the integral of 1 over x with respect to x. So we now have minus 1 over 4. We factorize minus 4 from the denominator and 1 from the numerator into bracket 2 plus 3v divided by v squared plus v dv is equal to integral of 1 over x with respect to x. So for the left hand side, we can now rewrite it to make our integration easier as minus 1 over 4 into bracket 2v plus 1 plus 1 plus v divided by v squared plus v with respect to v is equal to integral of 1 over x with respect to x. So we can now further simplify this as minus 1 over 4 into bracket integral of 2v plus 1 divided by v squared plus v dv plus the integral of 1 plus v divided by v squared plus v dv is equal to the integral of dx divided by x. So now we have to evaluate each of the integrals that we have here. So the first integral, we can evaluate it using use substitution method. So for the first integral, we have integral of 2v plus 1 divided by v squared plus v dv. So we can let u be equal to v squared plus v such that du dv is equal to 2v plus 1 and hence dv is equal to du divided by 2v plus 1. So we can now substitute this back and we have 2v plus 1 divided by u multiplied by du divided by 2v plus 1. And we have our integral to become integral of du all over u, and this gives us ln u. So on substituting u back, we have integral of 2v plus 1 divided by v squared plus 1 v to be with respect to v to be equal to ln v squared plus v. So that's the first integral evaluated. To evaluate the second integral now, we have second integral to be integral of 1 plus v divided by v squared plus v with respect to v. So this can be written as the integral of 1 plus v divided by v into bracket 1 plus v with respect to v. So this becomes integral of dv divided by v, and that gives us ln v. So we can now write our equation all over again. That gives us minus 1 all over 4 ln v squared plus v plus ln v to be equal to, on evaluating the integral on the right hand side, which is integral of 1 over x with respect to x, we have ln x plus ln c. Since ln c is also going to give us a constant, so we have minus 1 all over 4 ln v into bracket v squared plus v will be equal to ln xc. So this becomes minus 1 over 4 ln v cube plus v squared. Ln v cube plus v squared is equal to ln xc. So we now have ln v cube plus v squared to be equal to minus 4 ln xc, which is ln xc raised to the power of 1 raised to the power of minus 4. So ln v cube plus v squared is equal to ln xc raised to the power of minus 4. We can compare both sides, and we have v cube plus v squared is equal to xc raised to the power of minus 4. So in evaluating this, we have v cube plus v squared to be equal to 1 divided by xc raised to power 4, x raised to power 4, c raised to the power 4. So we can now multiply both sides by x raised to power 4. But before we do that, let's substitute our v to be equal to y all over x. So we have y divided by x all raised to the power of 3 plus y divided by x all raised to the power of 2 is equal to 1 divided by x raised to power 4, c raised to power 4. So we have y cube divided by x cube plus y squared divided by x squared is equal to 1 divided by x raised to power 4, c raised to the power 4. So we have y cube divided by x cube plus y squared divided by x squared is equal to 1 over x raised to power 4, c raised to power 4. So we can multiply all through by x raised to power 4. So we have x raised to power 4 into brackets y cube divided by x cube plus x raised to power 4 into brackets y squared divided by x squared is equal to x raised to power 4 divided by x raised to power 4, c raised to power 4. So we have xy cube plus x squared y squared is equal to 1 divided by c raised to power 4. We can write this 1 divided by c raised to power 4 as capital letter C, since the small letter c is a constant. So we can have this factorize xy squared. We have xy squared into brackets y plus x is equal to c. And with this, we have our solution of the differential equation y squared plus 2xy dx plus 2x squared plus 3xy dy is equal to 0. I hope I've been able to make it clear how to solve homogeneous differential equations and how to test for homogeneity. Thank you for watching this video. See you next time.